Hello, my name is Bailey Stevenson, and I am going to be presenting my Semester Systems Project Part 2, which will be over the cardiovascular system. The cardiovascular system is a pretty important system in vertebrae, as it is responsible for the movement of blood to and from the organs, which facilitates the movement of oxygen, nutrients, and waste. As vertebrae have evolved, a need for a more complex system in the cardiovascular system is needed. And this is especially true as environmental pressures have changed how vertebrae have evolved, specifically going from an aquatic lifestyle to a terrestrial lifestyle. As we continue to move forward on our tour of the cardiovascular system, we'll start with the early tetrapods, which are the Eusthenopterons, the Porolipiforms, and the Osteolipiforms. These guys had a pretty rudimentary circulatory system with a two-chambered heart and a single-loop circulation. This is similar to previous clades in their ancestral tree. This system was efficient for their fully aquatic lifestyle, relying on gills for gas exchange. The next species on our tour is the Tiktaalik, which is an important transitorial species between fish and tetrapods. Fossil records show that it had functional lungs alongside gills, indicating that it had an increased reliance on pulmonary respiration. Its cardiovascular system likely supported both oxygen sources, allowing for survival in low-oxygen aquatic environments. This adaptation highlights the early stages of circulatory modifications necessary for life on land, as these animals lived in shallow oxygen-variable aquatic habitats, which seem to be more like swamps and coastal wetlands. From the Tiktaalik, we now go into the early tetrapods, such as Ichthyostega and Acanthostega, which displayed a more advanced cardiovascular system. This included a three-chambered heart, and these adaptations helped separate oxygenated and deoxygenated blood, which improved circulatory efficiency as the reliance on the lungs increased. These tetrapods represent a crucial step in the shift from gill-based to lung-based respiration, and early tetrapods evolved stronger vascular structures and increased cardiac output to support higher metabolic needs on land. Additionally, increased oxygen availability in air compared to water allowed for more efficient gas exchange, reducing the energy cost of respiration and circulation. We now move to the reptiliomorphs, which refine the three-chambered heart, reducing blood mixing and enhancing oxygen distribution. This adaptation allowed for higher metabolic efficiency, enabling these species to become more active and explore new terrestrial environments. They had a partially septated ventricle that allowed for better separation of oxygenated and deoxygenated blood. And they had increased efficiency in oxygen transport, which also supported the development of more active predatory behaviors and more complex locomotion, reinforcing their success in diverse terrestrial ecosystems. The amphibians, like frogs and salamanders, retain a three-chambered heart supporting cutaneous and pulmonary respiration. This adaptation allows them to thrive in aquatic and terrestrial habitats. In the early stages of amphibian life, the tadpole possesses a two-chambered heart similar to fish, with a single-loop circulatory system that primarily supports gill respiration. As metamorphosis progresses and these animals become more terrestrial, the heart undergoes significant remodeling, with the atrium dividing into two separate chambers, while the ventricle remains undivided. The formation of a spiral valve within the conus arteriosus helps direct oxygenated and deoxygenated blood into separate circuits, enabling the development of a double-loop circulatory system. This transition allows for more efficient oxygen distribution between pulmonary and systemic circuits. Amphibians generally have a low-pressure circulatory system due to their reliance on both pulmonary and cutaneous respirations. Because they use pulmonary respiration and the lungs require a low-pressured system because they are delicate and a high-pressure system would damage them, and they are a three-chambered heart with mixing of blood and no efficient way to divert the blood to have two separate pressure systems, they must maintain a low-pressure system for proper pulmonary circulation. So that system ensures that the blood flow is adequate for oxygen exchange without excessive strain on the heart and lungs, making it well suited for their semi-aquatic nature, and this lower blood pressure limits their ability to sustain high energy activities compared to fully terrestrial vertebrae. We now move towards reptiles who have evolved modifications to their three-chambered heart that improve circulation efficiency. Squamata, which includes lizards, possesses an incomplete ventricle septum that helps reduce blood mixing, improving oxygen efficiency. Lizards generally have a moderate pressure circulatory system that balances activity with thermoregulation. Serpentes, or snakes, is a subgroup of Squamata, and they have further specialized circulatory adaptations, such as vascular shunting, which allows them to regulate oxygen distribution efficiently based on metabolic demands. Snakes tend to have a relatively low-pressure system compared to other reptiles, suited for their energy conservation and ambush predation strategies. So both of these adaptations enable reptiles to support thermoregulation, sustain their activity levels, and thrive in their diverse environments. So now we're moving to the testudines, which are the turtles. These guys have a low blood pressure system, which is good for slow movement. They still have a three-chambered heart, which has an incomplete ventricular septum. However, what's different about these guys is they have an intracardiac shunt, which diverts deoxygenated blood to the systemic circuit. This has a tendency, they now can separate their pulmonary blood flow from their systemic blood flow, and this is ideal for things like diving when they need to conserve and redirect oxygen-rich blood. They're able to shunt blood away from the lungs, so reduce that blood flow to the lungs to optimize that, and they are also able to retain carbon dioxide rich blood, which enhances gastric acid secretion in the digestion system with the possession of the shunt. So that is interesting and something different than we've seen in prior clades. The Samoria is a reptiliomorph that also possesses a three-chambered heart, which reduces blood mixing and enhancing oxygen distribution. They have a partially septated ventricle that allows for better separation of oxygenated and deoxygenated blood, which improves their systemic circulation. They have developed a more structured conus arteriosus with specialized valves that efficiently direct blood flow, and these modifications enhance cardiovascular performance, allowing Samoria and all reptiliomorphs to sustain extended periods of activity on land, which is an essential step in the evolution towards fully terrestrial amniotes. They have an increased efficiency in oxygen transport, and they are now moving into a more predatory behaviors and more complex locomotion. The Samora is very similar to all early reptiliomorphs, and there is not a fully complete record of them in the fossil record. So a lot of the information that has been pulled over for them has been due to their similarities with other early reptiliomorphs. Another species with a specific cardiac adaptation is found in the axolotl, which is an amphibian that retains its larval features into adulthood. Unlike most amphibians that undergo complete metamorphosis, axolotls maintain a neotenic state, including a heart that is functionally adapted to support aquatic and limited terrestrial respiration. Their three-chambered heart consists of two atria and a single ventricle with minimal separation, allowing for partial mixing of oxygenated and deoxygenated blood. The atrium is divided into a left and right chamber, which receives oxygen-rich blood from the lungs and oxygen-poor blood from the body, and a specialized spiral valve within the conus arteriosus helps direct blood flow, optimizing circulation efficiency depending on respiratory conditions. This dual adaptability provides a metabolic advantage in fluctuating environmental conditions and showcases an alternate evolutionary strategy in amphibian cardiovascular physiology. In summary, we have moved from a two-chambered heart with a single-loop circulatory system, as seen in early fish and stem tetrapods, into a more complex three-chambered heart, as seen in picture B, as provided there, that supports the separation of oxygen and deoxygenated blood, which in turn allows for better oxygen distribution to the organs and better uptake by the lungs, allowing these animals to become more and more terrestrial and more active, which has now led to a cardiovascular system that is meeting the environmental needs of the species. The evolution of the cardiovascular system is illustrating the relationship between physiological adaptations and environmental pressures, and these changes pave the way for studying more complex species and understanding how vertebrates adapt to different environments. And that concludes my presentation. Thank you very much.